Hey, welcome to another fantastic day in Calculus 3. We're going to be wrapping up mass of a planar lamina. Then we're going to be looking at another application of double integrals, which involves surface area of a surface. And then hopefully we'll get into something else too, like triple integrals. All right, as a reminder, here is the definition of mass of a planar lamina. And a lamina is like a thin film. It's a 2D, it's like a piece of paper. So if you've got some variable density of that paper, and it's given by some function rho, and so rho is a function of two variables, rho of xy, the way you set up the mass is, and you call it m, you do the double integral over the region, that's over your piece of paper or whatever it is you're trying to find the mass of, and you put your density function there in the integrand, okay? And I did an example last time. It was very wonderful, so I'm not going to do that one all over again. It was over a triangular region in 2D, and we figured out the mass for that. So the other example we're going to do is right here. We're going to find the mass of a lamina corresponding to the first quadrant of the portion of the circle. And that looks like a circle that's centered at the origin of radius 2, but we only want the first quadrant portion. So we want this portion here. That's our planar lamina right there. Planar lamina. And that's also our region of integration, R. When they go, what's the region of integration for the double integral? It's going to be this, quarter of a circle. Now, they are not giving us a density function for this one. It's a little tougher. They're not giving it to you outright. You're going to have to think it through, okay? They're giving you information, and you have to come up with it. So they're telling you that the density at any point in our region is proportional to the distance between the point and the origin. So this rho of xy is equal to some constant of proportionality times a distance. Okay, so if you pick a point here in our region xy, and you look at the distance between it and the origin, remember the distance is the square root of the sum of the squares of the differences between the x and y coordinates respectively. So the distance is going to be that. And that's your D right there. So what I'm saying is your rho of xy, that's your density function. And rho is a Greek letter. This is rho. And if you don't like it, you can use F. Like, well, I don't like rho. Why can't we just use F? Fine. Then use F of xy. Okay? It's going to be some constant of proportionality times your distance. Okay, now we're ready to set up the double integral representing the mass of this planar lamina. So the mass is double integral over the region, and we put our density function here in the integrand, and then some area element. So what do you think, folks? You see that this region is a perfect candidate for polar, and you're going to want to convert to polar. Well, how come? Because if you use the rectangular coordinates, then your dA will look like dy dx. And I don't know about you, but trying to integrate square root of x squared plus y squared, that's going to involve trig sub. And I'm not a fan of trig sub. I told you I don't want to do it. Not in this class. I do teach it in my Calc 2. So let's convert to polar. Polar coordinates, that is. Now on the region here, what's r and what's theta doing? Let's figure out the range here for r and theta. Well, r is just blooming out from the pole. That's the name for the origin in polar coordinates, all the way out to, I believe, a 2. Okay. Excuse me. No, I don't have COVID. Okay. And then the angle here looks like it's going from 0 to pi halves. Great. So when we iterate our double integral, we'll have r going from 0 to 2, and then the theta going from 0 to pi halves. And now let's convert our density function to polar. We still have the constant of integration. That's just some, some number. And then square root of x squared plus y squared. What does that convert to? Anybody remember? No? All right. This can be r. What else? Instead of dy dx, what do we put? I'll give you a clue. Be a pirate.
R dr theta.
Yes, r dr d theta. That's the area element for polar. And before you integrate, combine your powers of r into one big old power of r. And then you can integrate with respect to r first. And the antiderivative of r squared is r cubed over 3. And you'll evaluate that between the limits of 0 and 2. And we'll plug in our upper limit first. Looks like we're going to have 8/3. And this k is also a constant. So I'm going to pull the 8/3 k outside of our last integral. And then we're going to integrate the last guy. And it's understood to be a 1 there in the integrand. It looks like everybody's going, R. Yeah, good, good, good. All right, I'm treating you well. Thank you. I got a class full of pirates. That's just great. And so we get 8/3 k times pi halves. And then, of course, we can clean this up a little bit, right? 8 divided by 2 reduces. Is that it? Yeah, I think so. Okay, so 4 pi k thirds is the mass of that planar lamina that's shaped like a quarter of a circle. And we're done with mass of planar laminas. We'll look at mass again for solids coming up soon, but not yet. And so that wraps up the section for mass. Okay? What's next? Well, let's look at what you know how to do so far. Do a quick summary, and then we're going to get into something new. So when you're doing double integrals, what can you use a double integral for? Well, the first thing we look at for a double integral is area. Area in 2D, that is. So when you're using a double integral for area, you have a double integral over your region that you're trying to find the area of, and then the integrand is a 1. That's how you know it's representing area. And then you have an area element, dA. Now the area element for rectangular is either dy dx or dx dy. And the area element for polar coordinates is r dr d theta. Now I've had students ask me, do they ever flip the dr and the d theta? Because we had to do a lot of switching the order of integration, you know, from dy dx to dx dy. No, I'm not going to ask you to do any switching order for polar coordinates, okay? And traditionally, we leave the d theta as the outermost integral. So it's rare that you'll see d theta dr. Usually we do dr d theta. So stick to that. So what's another thing we can use a double integral for? Volume of a solid. So how do you know you're using a double integral to represent volume? Well, your volume is going to be your double integral. And there's a couple ways that you can do this, all right? You're going to have the region of integration, and then you're going to have something here in the integrand. Now, if your solid is the kind of solid that you have a capping surface here, given by z equals f of xy, and the base of your solid is here in the xy plane, and we'll call that region R, then only your capping surface will go into the integrand. Okay? Now, what's another volume type of problem you can run into? Okay, let's talk about that. On I think homework and a quiz that you had just recently, they had some z equals f of xy. I think it was some we had an upper capping surface that was like, I'll draw a sort of portion of it, like whoosh, like that. And let's say that was like 3e to the x minus y, just say. And then you might have a belly of the surface. So it may, your bottom of your surface might not be flat in the xy plane. It may be, you know, like let's say this is the belly, with some other function like z equals, I'm just, you know, using something from one of your quizzes. And then they might give you a base of your solid, you know, bounded by some stuff here and So this might be, I'm just drawing something here. Like let's say this is a region R, and your actual solid, if I had to draw the solid, would look like that, okay? So your volume is going to have the capping surface, the taller, minus the bottom of the surface, the belly. Like, this is supposed to be -4. If I'm using, this is a -4e. So minus the belly of the surface, like that. Okay, and then if they gave you the region of integration there in the XY plane, you'll just go over R. And so then you'll use an area element and so on and so on. So that's one way you could do a double integral. Another one that we did is where you had intersecting surfaces, and these two surfaces that I just showed you here do not intersect. So don't set the two surfaces equal to each other. That's not going to fly. Not for this example. Well, you did one that was like that. Yeah, I know. So another example where you have a solid you're trying to find the volume of is where it's got a top surface, a capping surface, and a belly. And this example here that we did in a previous lecture, these two surfaces actually intersect each other. Ooh, different from that last little thing I just showed you. And this one, since they didn't give you a region of integration, the region of integration is the projection of the solid onto the XY plane. And this is where you actually had to set the two surfaces equal to each other to figure out that intersection part. And then the intersection, for this particular example, after you set these two surfaces equal to each other, you got a circle. And I did it down here. And you got a circle of radius 2 centered at the origin. So that one, when you're doing something like that, you also do a taller minus shorter. You know, the capping surface minus the underbelly, if you will. So that's still the case. But then your region of integration, is, losing where I went. Your region of integration is the projection of your solid onto your XY plane. So there's different ways you can use the double integral to represent volume, all these different ways, okay? So now what? Well, there's one more thing that you know how to use a double integral for, and that's mass of a planar lamina. We just got done with that. So if you got a little thin film in 2D, little lamina, and you've got a density function, then your mass is equal to the double integral over that region, and then you put your rho of xy, that's just some density function, in the integram, okay? And if you are got your eyes wide open here, you may notice that the volume double integral looks very suspiciously similar to the mass of a planar lamina double integral, and you'd be right. Okay, now let's do a new application of a double integral. And there's going to be more, like, don't think this is it. We'll do some more when we get to the vector calculus module of the course. But there's one more that I'd like to introduce. Now, this is actually in the next chapter in our textbook, but I just want to let you know that in other textbooks, what I'm about to cover is found in this module. Now, how come you're making us do the next chapter right now? I'm actually only doing a piece of 17.6. I will finish 17.6 completely once we get into the vector calculus portion of the course. But the little piece of 17.6, that's what I want to cover now. And it's using the double integral to find surface area of a surface. So take a look at this capping surface right here. Okay, fine. What if I wanted to cover it with like some gift wrap paper? You know, how much square footage of gift wrap would I need to cover the top of it? It's kind of curvy, so it's like, you know, it's going to be kind of hard to cover. But the idea is what, you know, how much surface area is on that capping surface, so I can know how much material I will need to cover it, the wrapping paper or whatever. You know, coming up on that time of year. Okay, so here's the derivation of it. You got your surface represented by an explicit function of x and y, z equals fxy. And it's defined over some region R down here in the XY plane. In other words, R is the projection of that surface onto the XY plane. It's the shadow the surface would make onto the XY plane. Now, to find the surface area, here's what we're going to do. We're going to construct an inner partition, bunch of little rectangles there on the region, and little itty bitty rectangles. And then look at one little rectangle. Call it the rectangle subscript I. And then figure out the area of one of those rectangles. Now that's easy to do because we all know how to find the area of a rectangle. It's just length times width. So if you've got a little rectangle down here in the XY plane, it'll be, some delta Y times some delta X. Some little delta X would be, say, the width, and delta Y would be the length. So your little delta A sub I, that's your little tiny area of a rectangle, is delta X, delta Y. Fine. Well, that's not the surface, though. I thought you wanted to find the surface area of the surface. I know, we're getting there. Hold on. So, there's your R sub I. Now, pick the point that's closest to the origin. And then, come up here in heaven. Let's say your surface is the heaven right here. And you want to look at, well, they use this one here. So you come up here to heaven, and then you look at the ordered triple of that point. So if you're looking at the X sub I, Y sub I down here in the XY plane, the corresponding surface ordered triple is X sub I, Y sub I, F evaluated at X sub I, Y sub I. That's the Z coordinate. Okay, what of it? Well, we're going to construct a little tangent plane there. And you guys all know about tangent planes because we did that in the last module. And you know how to come up with the equations for these little tangent planes, right? We're going to pick a little portion of that tangent plane. Now, the reason why we're looking at a tangent plane is because it's flat. And we know how to find the area of a flat little rectangle. It's just length times width. And we're going to use that knowledge to approximate what a little patch of surface area would be. So the patch would be the actual surface area of that little patch right there would be delta S sub I. But that's too hard to find the surface area of that because it's so curvy. I don't know how to find the surface area of a curvy thing. Forget it. So here is the claim that you need to buy in order for you to get this and accept it. The little curvy patch, if I pick a small enough patch, has a very close, almost equivalent area as the little itty bitty tangent plane portion that we'll pick. So that's what you need to buy, that your delta T sub I, the area of that little tangent plane, is approximately, that's why they have the melted equal signs there, equal to your actual surface area of that little patch. Okay. Then, if you construct a whole bunch of tangent planes all covering up the surface, you're basically saying, and if you took the sum of all of those, that's a sigma, that means sum of all the ones going from 1 to n, it's going to be approximately equal to all the little sums of all the patches of surface areas. Okay, so that's what you need to buy. A good approximation. And now for the hand-to-hand combat. Okay, so I'm going to do a close-up. Here we go. Here's your delta T sub I. And it looks like a parallelogram instead of a rectangle. Okay, I'm going to blow it up some. So if I blow it up, what would it look like? I'm going to label the points. The point that's closest to the origin, I'm going to call it A. And then how about this point B, this point over here C, and this point B. Okay? Now the point that's closest to the origin would have the order triple X sub I, Y sub I, F evaluated at X sub I, Y sub I. The point B, since you're sort of heading in the Y-axis direction, he's going to keep the same X coordinate because he's still he's in alignment with X here. And the Y will be a little extra, so we'll call it Y subscript I plus 1. And then the z coordinate will be f evaluated at x sub I, y sub I plus 1. I know there's a lot of subscripts here. I apologize. It's okay. We're getting somewhere. Okay, let's do letter D before we do letter C. Letter D, his ordered triple is going to be, since you're sort of heading in the x-axis direction, the x will be different. His ordered triple is x sub I plus 1. His y coordinate is the same as A's, and his z coordinate is f evaluated at those guys. F evaluated x sub I plus 1, y sub I. And then finally, this point C has ordered triple x sub I plus 1, y sub I plus 1, f evaluated at x sub I plus 1, y sub I plus 1. Oh my gosh, this is yucky. Are we getting somewhere? Yes. And now I'm going to ask you to remember something from like the second week of class. Yeah, it's all coming together, people. What is that? I'm going to create two vectors here that make up adjacent side lengths of the parallelogram. So the adjacent sides of this parallelogram are, I'm going to call the AD, that guy there, we'll call him U. He's the same as AD. And the other vector, we'll call it V. And V is going to be the same as AB. So now let's, so why are we doing this? Because we know how to find the area of a parallelogram. It's the magnitude of the cross product. Remember that? Yeah, that's good to know for like maybe the final. So let's get U. How do you do that? Well, terminal minus initial, terminal minus initial. So if you look at the vector AD here, you're going to take the difference of the x coordinates, x sub I plus 1 minus x sub I, comma. Take the difference of the y coordinates, y sub I minus y sub I. Oh, that's going to be 0. And then take the difference of the z coordinates. You're going to have f evaluated at x I plus 1, y sub I minus f evaluated at x sub I, y sub I. Yuck. Now let's do some renaming. The difference of these x's, we're going to name it delta x sub I, because that's just a difference. And when you take the difference of the y's, you get 0. And now here's the weird part. See if you can get behind this. We're going to take that last component of this vector, and we're going to multiply it by a special version of 1, because you're allowed to do that. The question is, what is the special version of 1 going to be? Aha! So you still have this f of, oh, I had to do one extra thing here, sorry. What about this? I'm going to rename this. We know that since x sub I plus 1 minus x sub I was renamed to delta x sub I, if we solve this little equation for x sub I plus 1 by adding x sub I to both sides, we can replace this x sub I plus 1 with delta x sub I plus x sub I. Now you're probably thinking, oh my gosh, are you kidding me? No, I'm not kidding you. Yeah, you want to do it. This is getting more and more complicated by the moment. No, you're fine. Don't worry. This is what we have right now. So I told you I was going to multiply that last component by 1. So what's the 1 going to be? It's going to be delta x sub I divided by delta x sub I. That's the special version of 1. And then we've got our last angular bracket. But I'm going to move this one sort of underneath the difference. And the reason why I'm going to do that is because this thing here should remind you of something. And it turns out if we take the limit as delta x sub I goes to 0, this is the partial derivative of f with respect to x. It's the definition of it. Really? Yeah. So here's what we're saying. This vector u looks very special. Yeah. And we still have this delta x sub I out here. So let's save that for later. and move on. Well, now what? Well, I still have to get that other vector, the vector v over here. So we're going to do terminal minus initial between the points A and B. Yeah, got to get the other guy. And yeah, we're going to take a cross product. It's coming. So let's do the setup of V. Now remember, V is the same as AB in my little diagram there, my little mini parallelogram. So take the difference of the x coordinates, x sub I minus x sub I. Hey, that's 0. Take the difference of the y coordinates, y sub I plus 1 minus y sub I. Hey, that's delta y sub I. And then take the difference of the z coordinates. And like before, we're going to do a rename. Y sub I plus 1 is the same as y sub I plus delta y sub I. And we're also going to multiply this last component by a 1. What's the special version of 1 going to be this time? Well, glad you asked. It's going to be delta y sub I over delta y sub I. So let's do that. Let's do some cleanup here. So if you look at this, and you take the limit of this as delta y goes to 0, this is the definition, delta y sub I. This is the definition of the partial derivative of f with respect to y. So the other vector looks like this. Okay, now area of a parallelogram is going to equal the magnitude of the cross product. So first we have to go get the cross product. Yeah, let's do it. Remember, I like to see the 3x3 determinant method in my class. Also, I just want to remind some of us are getting a little lazy about showing that 3x3 determinant. I want to see strong bars, and I want to see I hat, J hat, and K hat in the top row. I don't like it where your bars are drooped down. Like if you put I hat, J hat, and K hat in the top row, and then you put your bars lower, I'm going to take off a point or 2. Bad notation. No, the I hat and the J hat and the K hat are in this determinant. So please show it. And notation does matter. When you get to your linear algebra class, you'll thank me later. Okay. So then I'm going to put the components of the u vector in the second row, delta x sub I, 0, and the partial of f with respect to x. Woo! Evaluated x sub I, y sub I times delta x sub I, and then the components of v on the bottom row, 0, delta y sub I, partial of f with respect to y, evaluated x sub I, y sub I, times delta y sub I. Okay, so you know you're going to have a 2x2 I hat minus 2x2 j hat plus 2x2 k hat. Show me. So this is going to be, 0. I'm going to do a little bit of abbreviation here. Fx times delta x sub I, delta y sub I, fy, delta y sub I. This one here is going to be delta x. Fx, delta x sub I, delta y sub I, fy, delta y sub I. And the last 2x2 is delta x sub I, 0, 0, delta y sub I. Fine. Okay. So here we go. You're going to go 0 times that. Whoa. Is going to give you a 0. And then minus the fx times the delta x sub I, delta y sub I. Okay. That's times your I hat. Minus, let's look at this next thing here. This thing, something is, there's a speed up somewhere. Hold on a minute. Middle determinant, this has to be a 0 right there. Copied it down wrong. Okay, so now when we do it, we're going to get this guy times this guy minus the minor diagonal, but that's 0. So you're going to end up with Fy, x sub I, y sub I, delta x sub I, delta y sub I, minus 0, j hat, plus, and then the very last determinant, you've got delta x sub I, delta y sub I, minus 0, we won't even write it, times your k hat. Whoa, this is a mess. I'm going to try to rewrite this as in component form, looks a little cleaner. What am I going to have? I'm going to have the minus fx, x sub I, y sub I. And what I want you to notice is that every single one of these components has a common factor of delta x sub I, delta y sub I. I'm going to factor it out because I can. Put it out here. And so the middle guy ended up being, after we factored out the delta x sub I, delta y sub I, we had minus the first partial of f with respect to y. And then after we factor out our common factor, that last component is a 1. Okay, now. And this is just some scalar out here. This is your area. So now this is your cross product. I want to take the magnitude of this cross product. So the magnitude is going to be the square root of the sum of the squares of the components. And you could have left the delta x sub I, y sub I in there, but then after you're factoring out again, it's just going to be a scalar. And when you square a negative, you guys know it is going to be positive. So I'm just not even going to bother writing those negatives in here like so. Okay. Now, what is the surface area? What are we saying our surface area is going to be? The surface area is approximately, that's approximately, oh boy, feels like Friday. The sigma sum of all the little itty bitty tangent planes. So that's going to be equal to sigma, I going from 1 to n, of this big old square root. And then this delta x sub I, delta y sub I, that's your little area of your rectangle there in your xy plane. I'm just going to call it delta a sub I. And so you've got, I'm going to rewrite the radicand so it looks a little prettier. Put the 1 first, looks nicer. And there is your, oh. Here, now my erase tool is working. Thank you. Ha ha. Being a little slow. Here we go. Okay, so that's getting squared. Okay, so now what? Well, now you're going to take a limit as your partition firms up down there in the XY plane. So as the norm of the partition goes to 0. Woo! And then what do you end up getting? Well, you end up getting your definition of surface area. Because remember, we agreed that we were going to buy that one little patch of surface area. A good approximation of it is one of those little tiny tangent planes. So we just added them all up, and now we get the definition of surface area. So here it is. And this is what you're going to bring, to your quiz this weekend. You're going to want this definition. You don't need to rederive everything I just did. If you were staying awake that whole derivation, congratulations. So if you've got your capping surface, z equals f of xy, and that's what you're trying to find the surface area of. And it is continuous over the region R. That's the projection of it in the XY plane. Or somebody might give you the portion of it that they want in the XY plane. Then your surface area is given by a double integral. And here's the weird part. I'm going to introduce some really weird notation. Please try to be comfortable with it. I know it's weird at first. Instead of an R down here, you're going to see an S. It stands for surface, because this is a surface integral. And then you're going to see ds. It's a big S. What the heck? And that means surface area element. This ds is a surface area element. Well, what the heck is the surface area element? It's not what you think. It's what we just did. So this surface area double integral, you can't evaluate it. You have to rewrite it as a regular double integral. Well, how do I do that? The way you do it is the S down here turns into an R. And usually your R is the region in the XY plane. And then the surface area element is this humongous, ginormous radical, square root. 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared. And then you put dA out here, the regular area element, like dx dy or dy dx. Or if you're doing polar, r dr d theta. And then hopefully that integral is integrable, because sometimes it might not be, because sometimes if you get a hellacious looking square root, it could be like, yeah. Okay. So there you go. Surface area. Boy, yeah, I do a bunch of stuff here. What the heck? Okay. What are some other integration that you've done? When you did the length of along an x-axis, this is kind of cool, people. Like you just look at length along an x-axis. What's the length between A and B? B minus A. But can't you do that with an integral? It's a little bit of overkill for sure. I get it. But if you integrate 1 with respect to x and your limits are A to B, you will get the length of that integral, that straight line. What about arc length? And you did this when you took a Calc 2 class. Let's say you have a function here, y equals f of x, and somebody wants the length of the arc between A and B right there. We call that little s, and the arc length is the integral going from A to B, 1 little ds, that means the arc length element. And the arc length element, you learn this in Calc 2, is the square root of 1 plus f prime of x squared. How about area in the plane? Using a double integral, you got a 1 over the region dA. Now you know surface area in space. Integral over s ds. ds is the surface area element. Kind of looks like arc length, doesn't it? Sort of, kind of. Okay. Let's do some examples. I've got 3 examples for us, okay? Find the surface area of the portion of this plane that lies above this circle in the first octant. So let me draw what they want, because it's kind of weird and it is confusing. And when I put this kind of problem on a quiz or an exam, students get confused and they get the wrong answer because they didn't even really understand what was being asked. So watch closely. We all know how to graph planes, find the x-intercept by setting y and z equal to 0 and so on and so on. So you're going to find out that the x, y, and z axis intercepts are all 2. So this is a portion of the plane in the first octant. Do we want to find the surface area of this whole thing? No. You misread the problem. Oh, what do they want me to find the surface area of? Hang in there. I'm going to draw it. I'm getting there. You only want a portion of this plane. What portion? Well, first, draw they want you to draw going on in the XY plane. Well, in the XY plane, it's just a little unit circle here, So if I draw that unit circle here in 3D in the XY plane, it's down here. Okay? Now what? Well, in the first quadrant, which is just this portion of the circle, we want the portion of the plane that's hovering over that little quarter of a circle. So if I had to actually shade the portion of the plane that's hovering over that circle, it would be this, it kind of looks like a pizza slice, actually. Ha ha. Yeah, we want the surface area of that. Of this kind, it kind of looks like a pizza slice. That's the portion of the plane that's hovering over that quarter of a circle. I hope I'm making myself clear here, because if you don't get that, and then you set up the wrong surface integral, you're going to blow the whole thing, and then you're going to get all frustrated. And it is frustrating when you get the wrong answer. I get it. It is really annoying. Like, why? I thought I got this stuff. Okay, first get the capping surface as an explicit function of x and y. And that's easy by just subtracting the x and the y from both sides of the equation. And why do we do that? Because if you look at the surface area formula, oh dear, it's way up here. Oh, where is it? Where is it? Where is it? Oh my goodness, here it is. You have to set up this horrific looking radical. So the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared. So what, who's your function f that you're doing business with? You got to make sure you're straight on that. It's not the circle. So your fx is just going to be, that's easy, just -1. And your fy is also -1. Okay, fantastic. So then this big old square root that we're going to have to put together here, because that's going to be the integrand of this surface area thing, for us is going to be square root of 1 plus a -1 squared plus, hey, this is going to be a constant. Cool beans. Does that always happen? No. So the surface area is going to be the double integral over the region R, and the region R is the quarter of a circle. And then we've got our, our big old radicand, but we agreed that after simplifying this one, it was square root of 3, and then an area element. Okay. I claim that since the region of integration is a quarter of a circle, we want to convert to polar. Or do we? There's two ways to do this problem. I'm going to call this way number 1. So you go, okay, integral square root of 3, and over the quarter of the circle, well, the area element is r dr d theta, and r is going from 0 to 1 on that cute little unit circle. And since we're only in the first quadrant, theta is only going from 0 to pi halves. And you can go ahead and integrate this, and you'll do it. It'll be fine. What's another quick and dirty way to do this? And I want you to notice this, because you're going to be doing this on a future exam or even the final, and I'll let you do it the quick shortcut way. Watch closely if you like shortcuts, because this is for you. I noticed that when I pull the square root of 3, so this is way number 2, outside of the double integral, let's say we didn't convert to polar. Let's say we had this, and we have the area element, and it's over the region. When you have a double integral and there's a 1 in the integrand, this represents area. That's what you use it when you're using a double integral to represent area. You just have a 1 in the integrand. Well, what area are we talking about? In this case, a quarter of a circle. Okay, fine. Which quarter of a circle? Well, we already showed you right here. This little circle that had a radius of 1. So I'm going to cheat. And I'll let you cheat if this is the case. So I'm going to do my way number 2. I'm not going to set up the rest of this double integral. I'm just going to go square root of 3 times the area of a quarter of a circle, quarter of a unit circle, because that was a radius of 1. And you already know how to find the area of a circle. It's pi r squared, right? But you're going to take 1/4 of that. So 1/4 of pi, and the radius of that unit circle is 1. And don't forget, you still have the square root of 3 here. That doesn't go away. And then your final answer, and this is your surface area, is square root of 3 pi 4 square units, because we are doing an area. In this case, a surface area. And we're done with this problem. Pretty cool, huh? Don't you like the shortcut? Who doesn't like the shortcut? I should ask. Ha! Come on, people.
Wow.
Wow, there you go. Thank you. Okay, let's do another surface area problem that's a little trickier. So I got example 5 queued up. We want to find the surface area of the portion of a paraboloid. Paraboloid. And this paraboloid, you can use GeoGebra to graph it as an upward facing paraboloid that has its vertex at 1 on the z-axis. So this is the surface that we want to find the surface area of. But we don't want to find the surface area of the whole thing. It goes on forever. We only want a portion. The portion that's hovering over a unit circle down here in the XY plane. So if we only look at the surface area that's hovering over that little unit circle, we're only going to look at a portion of this paraboloid. So it's going to sort of look like a little cup. That's it. So the bottom of that cup is what we want to find the surface area at. That's it. Okay. So remember the z equals 1 plus x squared plus y squared. That's your capping surface. There's your f. So you want to go get the partials because you're going to need those to set up that ginormous radical. Okay. So your surface is going to be the double integral over the region R, and that's the circle, the unit circle there in the XY plane. And then you've got your big ginormous radical. That FY should be a 2y. My apologies. I wrote it down wrong. dA. Okay, so this is going to look like square root of 1 plus 4x squared plus 4y squared. Can you guys say convert to polar? Because we're going to need to. This one does not have a shortcut. Sorry. No shortcut here. Because you're not going to get it to be where it's a double integral where there's a 1 only in the integrand. But I do want to convert to polar because I certainly don't want to replace the dA with dy dx and then try to do trig sub. That would be horrible. So convert to polar coordinates. Look at this radical here. If you factored out a 4 from the x squared and y squared terms, it becomes the square root of 1 plus 4r squared, because x squared plus y squared converts very quickly to r squared. The area element for polar, be a pirate, r dr d theta. And then what is the region of integration? The region of integration is down here in the xy plane, and it's just a unit circle centered at the origin. Then r is just going from 0 to 1, and theta is going all the way around 1 revolution, 0 to 2 pi. Let's go ahead and do this integration by hand. We're going to use the power rule with u substitution. So you're going to let u be 1 plus 4r squared, the stuff that's under the radical, and du is 8r dr. Good news and bad news. Good news, there's already an r and a dr in the integrand. Yay, yay us. What's the only thing that's missing? An 8. If we had an 8, we could keep going. Well, good news. I'm just going to multiply or put an 8 in my integrand, provided I multiply the front of the whole thing by the reciprocal. And then I'm really just multiplying by a special version of 1. Now, the intermediate step, I want to see it. This inner integral is now looking like u to the 1/2 du. And you still have the outer integral. Okay, I want to see that. I want to see the next intermediate step. This integrand is easy to integrate because you use the power rule. So you'll just get 2/3 u to the 3/2. And then I like you to back substitute for u. And I'm going to pull the 2/3 out because it's just a constant multiple. And I'm going to evaluate this 1 plus 4r squared to the 3/2 between the limits of 0 to 1. Ooh, yuck. And then we still have to integrate the last guy. From 0 to 2 pi. Be careful because this 0 is deceiving. You're like, I'm not going to plug it in because everything goes to 0. Well, not this time. So you're going to go 1 plus 4 times 1 squared to the 3 halves minus 1 plus 4 times 0 to the 3 halves. This whole mess, d theta. And you'll get some weird numbers. Like this is 5 to the 3 halves, which is kind of horrible. And then 1 to the 3 halves is nice because that just is the same as 1. And this is just a weird number. So pull it out in front of the entire integral. And then integrate 1 with respect to theta. And that's just going to be, and by the way, this 5 to the 3 halves, if you want, you can simplify it to 5 square root of 5. That's okay. Same. And you're going to evaluate theta between 0 and 2 pi. So your final answer, the exact answer, is this weird number. I'm going to reduce just a little bit because 2 divided by 12 is 1/6. It's going to be 5 square root of 5 minus 1 over 6. That whole mess times pi square units. I know, we're doing a surface area, remember? Okay, so what was the point of this one? Well, a couple things. First of all, you're doing surface area, and you're using a double integral to represent surface area. So it involves this thing called the surface area element, which is this huge radical, 1 plus the sum of the squares of the partials, dA. And this one was nice because it ended up, when we converted to polar, we just used power rule. Worked out. Beautiful. This next example I'm doing for you as a favor, because I want you to see even more integration. Integration can be tough sometimes for students in Calc 3. You're all graduates of Calc 2, so you saw a lot of this integration, right? You're comfortable, hopefully. So check out this last surface area problem, and then you'll get to do some more on your own. You're going to find the surface area of a portion of a sphere that lies inside the cylinder. This is weird because you got to figure out, you're not finding the surface area of an entire sphere. There's an easy formula for that. Heck, you wouldn't need a double integral for that. You're finding the portion of the surface area of a sphere. And the portion that sits inside of a cylinder. Okay, so let's cue it up. First up, what does that sphere look like? Well, we learned about equations of spheres 2 months ago. That's a sphere centered at the origin of radius 5. Great, let me try to draw it. We don't want the whole surface area of that sphere. Be careful. Now, this cylindrical surface, x squared plus y squared equals 9. If you draw the generating curve, which is the circle in the xy plane centered at the origin of radius 3, and then you whoosh it in the direction of the missing variable, which is z, you get this cylinder. Okay, great. Yeah, so what? Well, what is the portion of the sphere that lies inside this cylinder? And we just want the surface of the sphere. So I claim that the surface of the sphere that we want, that's inside this cylinder, are the caps. This cap right here, that's the North Pole. I'm calling it the North Pole, haha, as well as the South Pole. North Pole plus the South Pole. So the surface area we want is the surface area of the North Pole plus the surface area of the South Pole. Now, because of symmetry, I claim that we can just figure out the surface area of one of the poles and multiply by 2. So our total surface area, to make it a little easier to do, is 2 multiplied the surface area of the North Pole. Let's just do that, and that way it'll be a little cleaner. Okay? So that's our plan to tackle this problem. Yeah. So what of it? Well, first we need the capping surface written explicitly. So what you're going to need to do is you're going to need to solve the sphere equation for z, and it's not going to be pretty. So after subtracting the x squared and y squared terms from both sides, you know you're going to square root both sides. Don't forget your plus or minus. And I get two answers. Well, which one do we want? Well, the one we want is the positive square root, because the negative square root would be the bottom hemisphere, and we want the top hemisphere. So we'll take the positive. So our z is positive square root of 25 minus x squared minus y squared. Fine. Now what? Well, if I were you, I would rewrite that with exponents, because you know radicals are evil. That's what I always say. So your z, which is your fxy, and I'm doing this so it'll be easier to take the partials. So let's go get the partials. You're going to need the chain rule. Clean that up. I don't like negative exponents. Always clean it up and reduce. These twos cancel. When I rewrite with positive exponents only. And just to make it look really clean, let's put the radical back in, because when you raise something to the 1/2, it's the same as the square root. Fine. And we're going to do the same thing to find the partial with respect to y. Use the chain rule, reduce, and rewrite it. Okay, are you ready? Big S, that's surface area, is going to be the double integral over the surface ds. That's what a surface integral looks like. But you've got an S down here. We'll do more of those when we get to vector calculus. But this is your first introduction to surface integral, a baby one. Baby ones where you just have a 1 in the integrand here. Okay, but then this surface area element, remember that ds is really the square root of 1 plus fx getting squared plus fy getting squared dA over the region of integration. But for us, now that we got the fx and the fy, it's going to get a little messy, people. I hope you don't like freak out. It's going to test your algebra skills. You know, the way you find out if you really know algebra is you take calculus. Ha ha! Yeah. Boy, that looks horrible. Yeah, I know. So before I do anything, because we are going to convert to polar, but not yet. Let's do the algebra. Let's look at this radicand only. So consider the radicand. Let's just do some work on it to clean it up. So what does it look like? Well, after we do the squaring of the last two terms, you know, when you square a radical, the radical goes away. Ooh, that's sweet. We got that mess under the radical. But I want to combine all three of these terms into one big term. But I got a problem because the 1 is messing me up. Well, let's multiply the 1. Well, first turn the 1 into a fraction by giving him a denominator, and then multiply him by a special version of 1. That would be 25 minus x squared minus y squared divided by 25 minus x squared minus y squared. Okay, then what? Well, then this fraction here, all three of these fractions have a common denominator. So you're like, sweet. So that means you can write all three of them with one denominator, and then just take the sum of all the numerators. Okay, and then you see what happens that's kind of nice? What kind of happens that's nice here? We're hoping it cleans up a bit. The x squared, y squared terms cancel, and we're left with just this. And remember, that was under the radical. So what do we have so far? So far, our surface area is going to look like this. Okay, now what is R? That's the region in the XY plane. Well, what the heck was that? That was the cylinder, the cylindrical surface. The x squared plus y squared equals 9 type of deal. That's your R. So then what? Well, convert to polar. Come on, let's do it. Because you're going to want to. I'm going to do a little bit of extra here. When you take the square root of a quotient, it's the same as the quotient of square roots. And then I'm also going to factor a negative out from the x squared, y squared terms. Why? Because when I convert everything to polar, it's going to be really sweet. And square root of 25 is just a 5. So the denominator is square root of 25 minus r squared. And then the area element for polar is, be a pirate, r drd theta. R is going from 0 to 3, theta from 0 to 2 pi. And I claim that this is integrable with respect to r. I'm just going to pull the 5 out because it's just a multiple. So this right here, you're going to use the power rule with some u substitution, you know. And RDR already exists in the integram. The only thing that's missing is a factor of -2, but no problem. You can put a factor of -2 in there, provided you multiply by its reciprocal. And so now what do we have? And then that middle inner integral looks like 1 over square root of u du, like so. But that's the same as the integral of u to the -1/2. And then when you use your calculus 1 power rule on that, it's 2u to the 1/2. But then you want to, in this 2, I'm just going to pull it out front. Then this u to the 1/2 is the same as square root of 25 minus r squared, where r is going between, what the heck, 0 to 3. I think I forgot my 5 somewhere in there. Where'd my 5 disappear also? Yeah, he's still there. Sorry. This 5, I don't want to forget him. Poor guy. I know. Yeah, like, okay, we're almost done. Yeah. So what do we have out here in the front? Yeah. Hang on a second. Okay, we're good. Okay, so now you're going to substitute this upper limit there, and you still are going to have to integrate with respect to theta once you're clear with this one, right? God, this is taking us forever and a day. I know, I'm sorry. So what do we have here? This cleans up to -5. This is going to be square root of 25 minus 3 squared minus, and then don't forget to plug in the 0 like this. Big mess. Hey, but these radicals end up being kind of sweet. This doesn't always happen, okay? Don't get too excited. But hey, if it does, you know, square root of 16 is 4, and square root of 25 is 5. So 4 minus 5 is equal to -1. Pull that out in front. So -5 times -1 is +5. And then you're just going to integrate 1 with respect to theta, and that's just theta. And so I get 10 pi. Now remember, this is the North Pole. So you're going to have to multiply by 2 to get both poles. So multiply by 2 to get the entire surface area. And I get 20 pi square units of surface area. Woo! Okay. I like that problem because it does involve spheres, and then we are going to care more about spheres a lot when we get to spherical coordinates next week. Okay.